Hello, this is my first demonstration video serving as an introduction to my software called PETTaLS, which stands for Perfect Exciter and Tactile Transducer Loudspeaker Simulator. This is something that I developed based on probably 10 or 11 years of research that I've been doing as a professor in electrical engineering into flat panel loudspeakers or distributed mode loudspeakers. I have quite a few papers on all of the math behind all of this in the Journal of the Audio Engineering Society and Journal of Acoustical Society of America and IEEE conferences and things. I doubt anyone's interested in any of that, but if anybody is, I can always post those links, or you can find them on my website, mozartandcircuits.com. What this software is designed to do is let you put in a bunch of parameters about both a panel that you want to turn into a loudspeaker and the exciters that you want to attach to that panel. So for the panel, you can choose the materials, the length and height of that panel. So length in the x direction in meters, length in the y direction in meters, the thickness of the panel, the boundary conditions of the panel, so that's how it's attached at the edges. I'll go through some of these things in more detail in subsequent videos. Right now I'll just say S stands for simply supported, C stands for clamped, F stands for free, and then the 4 letters stand for each of the 4 edges. So SSSS is simply supported on all 4 edges. CCCC is clamped on all 4 edges, and so on. Then stands, so like a free panel, you can't really have a free panel just free in space. You can in math equations, but you can't in real life. So sometimes we attach stands to things like that. So I can have corner stands for the free panel. I could have a center stand for the free panel. I can also have a center stand for like a simply supported panel. That will really screw with it. That's not, I wouldn't recommend that, but you can do it. I've programmed in up to 4 exciters that you can simulate. I can do more. I could do infinite number of exciters, but I don't have infinite space on the GUI here. So right now I've just done 4, and then these locations are normalized to the dimensions of the panel. So like 0.4 is 40% of the way along the x dimension is where the exciter goes, and then 40% along the y dimension is where that's where that one exciter goes. So for exciter type, I have 2 exciters from Dayton Audio programmed in, the DAEX19CT-4 and the DAEX32EP-4. One small exciter and one large exciter. And then additionally just point force. The exciters really have 2 effects. And the first effect is that their resonant characteristics affect the low frequency response of the panel. And then the shape of the exciter affects the high frequency response of the panel. So the point force has neither one of those things. It neither affects the low frequencies or the high frequencies. So this, if you just simulate point force, it can give you an idea of like what the acoustics of the panel would be in an ideal sense without the effect of the exciter complicating things. But ultimately, it's not super realistic. Okay, so let's start off with a fairly average simulation, I would say. Let's do acrylic. I'm going to do 6mm just because I know that that simulation doesn't take forever. And then let's not do a square panel just because square panels are kind of bad. Let's do a 0.2 meter by 0.3 meter. That's not a very big panel, but it'll simulate quickly. I wrote this simulation so that it simulates up to 50 kilohertz, just to be safe, no matter what the dimensions of the panel. And with smaller panels, that happens more quickly than with larger panels. So this might not sound the best, but it'll at least simulate quickly, and it'll just show off what we want fairly well at first. Okay, boundary conditions, simply supported on all four edges, no stands. Exciter location, let's do 0.3 and 0.3 for the first simulation. And point force. Okay. Okay, we have our results. Up here in the upper left is a diagram of the panel and the exciter on the panel. You can sort of see the little point force is right here. It's hard to see without using an actual exciter. This is the surface velocity map, and I can select different frequencies using this slider. So you don't really pay attention to the indices down here. I'm just simulating 512 frequency points, but that doesn't correspond to the actual frequencies. So the actual frequencies are here. So at 25 hertz, the surface of the panel is vibrating like this. Yellow is more excursion, blue is not moving at all. So as I go up in frequencies, you'll start to see more complicated shapes emerge. And then once I get up into really high frequencies, the vibration should just be localized to the point where the force is. Yeah, up here. Okay, so over in this graph, the solid line is the average acoustic response in decibel sound pressure level at the horizon from minus 90 degrees to 90 degrees. So there's no elevation component to that, which, you know, is reductive a little bit, I suppose. That axis is over here. So for, and I'm not inputting a voltage or anything. This is just relatively comparative. It's with like a reference force. So if you wanted to compare that to voltage, you'd have to look up like the force factor of the transducer, BL, and then convert that back. I'm just using a reference force, so the force is always the same, and it's a force that is usually, you know, at a normal volume, let's just say. So if you turned your amplifier up or down, this frequency response would just go up or down. I'm not really concerned with like how much voltage I have to put in other words. The dotted line down here is the frequency response of the surface velocity. So these aren't exactly one-to-one. They tend to have a lot of the same peaks, but sometimes peaks in the velocity of the surface don't show up as peaks in the frequency response, like this one. What frequency is that at? 332 hertz. So let's see what's going on there. This one. Yeah. And so that one doesn't cause, that would cause an effect in the elevation response, but since we're not looking at elevation in this black line, it doesn't have really any effect on the average horizon level frequency response. So that's kind of interesting. Okay, so this red line right here is what we call the coincidence frequency, and that's when let's find out what that is. It's about 6,000 hertz-ish, so let's find where that is. Somewhere around here. So 6,000 hertz is when the wavelength of these waves on the panel is equal to the wavelength of that same frequency in air. So below that coincidence frequency, the wavelength on the panel is shorter than the wavelength in air, and above that frequency, the wavelength on the panel is longer than the wavelength in air. And right at that coincidence frequency, the radiation from the panel is pointing parallel to the surface of the panel. So it goes out at the edges, and it doesn't beam out towards the center. And so we can see on the polar map that happens right around here. And then as you go up from the coincidence frequency, that beaming from the edges starts to move in towards the center. Okay, so that's the coincidence frequency. That usually causes some increase in average acoustic radiation right at that frequency. But again, it's even though this is just the average, that peak tends to be more towards the beaming towards the edges. And then above that, usually the average acoustic response goes, down quite a bit. So coincidence frequency is usually a good thing to try to push higher. And by making panels thinner, you can push that higher. Okay, so down in the lower left then, I already kind of referenced this, the polar radiation map. So this shows the loudness of the speaker, more or less, in sound pressure level, SPL, from 20 hertz to 20 kilohertz on the x-axis, and from 90 degrees to minus 90 degrees on the y-axis. If you're used to doing professional loudspeaker measurements, I'm sure you've seen a lot of these types of graphs. These panel loudspeakers don't really look anything on these graphs like traditional cone loudspeakers, so these do look kind of weird. Yeah, so this bright line here corresponds to this mode at 174 hertz-ish. Let's go find that. That should be, yeah, this guy. So that's this mode, and that causes this bright line here. Let's see, this funny pattern right here is at, what, 541 hertz? So here, let's try to find, does that correspond to anything here? Is that this one? Yeah, that's pretty much that one. So let's find out what's going on there. Oh yeah, that makes sense. It's this guy, that mode. Yep. So that mode causes this radiation pattern. And then, it's some of these low frequency modes and radiation patterns, it's easy to tell what's going on. As you get higher and higher in these frequency, it's really hard to tell what's going on anymore. Okay, so I just want to show then what the effect of all of these different choices or the design parameters or design options has on these results. So if I click on compare results, I can save the old results here and then compare them to a new set of results. I don't like doing that more than twice because the graph gets really crowded. So every 2 sets of results, I'll clear that. So let's switch from point force exciter then to an actual exciter and compare these old results to the new results with all the same other parameters staying the same. Okay, cool. So here's our new set of results. The dotted line is the new acoustic frequency response. We can see over here the exciter now has a ring shape because that's the approximate ring shape of this exciter as it couples to the panel. So the low frequencies changed a little bit. We've got this extra little resonance here, and that comes from the exciter itself, and then it drops off a little faster. But for the most part, a lot of this mid-range stuff stayed the same. And then it looks like at high frequencies, it drops off a little bit faster due to the exciter. Okay, so now let's just change the location of the exciter. So 0.4 and 0.4, say. And now let me demonstrate that that is going to have an effect on the frequency response. And again, I'm going to, just to keep this from getting too crowded, I'm going to refresh the results. So if you want to compare the new results to these old results, you'll just have to rewind the video. Okay, so there's our new results for the new exciter. We can see that the exciter moved a little bit. The modes probably haven't changed a whole ton if you scroll through. Up at these high frequencies, obviously the vibration is now isolated around where the new exciter placement is. These frequency response results did change a little bit, but not a ton. So exciter placement does have an effect, but not a, sometimes has an effect, not always a huge effect. Let's plop a second exciter in there, and let's put it in the upper right corner just for the fun of it. I have no idea what this is going to look like, but now we'll have one exciter that's kind of in the middle and one exciter that's in the corner, and we'll compare these to the previous results. And these exciters are doing the same thing, so they're both pushing on the panel, like they're wired in parallel in this case. Okay, so that didn't have a huge effect, I guess. We can see the dotted line more or less overlaps quite a bit with the solid line, so the old results and the new results are not terribly different. Let's look at what's going on at high frequencies. Yeah. So, I mean, we have two isolated areas of vibration. Yeah, so that had, some effect on the frequency response, not a ton. Okay, so now let's show the effect of different boundary conditions. So let me do a really radically different one. Let's just do all free edges with corner stands. So this means a free panel that its edges are not attached to anything, but it has little stands in the corners. So the corners can't move. And I got rid of that second exciter. All right, so we have our results. That's a pretty radically different frequency response now with the free panel and the corners unable to move. So let's look at some of these modes now. 50 hertz, there's something going on, so let's try to find that. Yeah, that's this. That's where it looks like the whole middle of the panel is bending. Let's see what's going on here. So 396 hertz. It looks like this mode. So there's an interesting vibrational mode right there that causes not only this peak here, but also this omnidirectional radiation characteristic, which is then followed by a pretty sharp drop in radiation as we go up to these higher frequencies. That's pretty interesting. You can see that the coincidence frequency hasn't changed. That's only dependent on the panel materials, so changing any of this other stuff isn't going to change that. Let's compare that to a square panel. So instead of 0.2 meters by 0.3 meters, let's do 0.3 by 0.3. So square panel now, and we'll compare that to the non-square panel. But with the same exciter, normalized exciter location and the same boundary conditions and exciter type and everything. Okay, so let me move the vibrational results down a little bit. So shifting or changing the dimensions of the panel did change the frequency response somewhat. Some of the low frequency stuff didn't change that much, but as we go up in the frequencies, it seems like everything got shifted a little bit more. Again, the coincidence frequency didn't change. We actually have a nice region here of sort of flat response until we get to the coincidence frequency, and then everything starts getting screwed up. The coincidence frequency, again, causes this kind of increase in average radiation followed by a pretty sharp decrease in average radiation. Again, that's something that we want to try to probably push higher. So as we go up in frequency, we can see that the vibration becomes localized around the exciter again. Okay, so let's demonstrate then pushing that coincidence frequency higher by making the material thinner. So I'm going to go from 6 millimeter thick acrylic to 5 millimeter thick acrylic. And I'm generating new graphs just because I don't want this to get too crowded. Okay, so we've got our results now. 5 millimeter thick acrylic, so thinner acrylic. The coincidence frequency got pushed up to, it was at, I think, 6,000 hertz. Now it's at 7,300 hertz, so it only got pushed up a little bit. Now we have a blue line too, and the blue line is when the dimensions of the exciter start to affect the acoustic radiation. So at high enough frequencies, the exciter is actually larger than the wavelength on the panel and causes some cancellation. And so the blue line is where you get lowered radiation because of the dimensions of the exciter. So that's only starting to become impactful at the very highest frequencies now, at 5 millimeter thick acrylic. Unfortunately, there's a trade-off. As you make the material thinner, the coincidence frequency goes up, but this critical frequency where the exciter starts to become important goes down. You can actually get those two to overlap at the right panel thickness, and they somewhat cancel each other out, but they still both will have a pretty sharp decrease in average acoustic radiation above those frequencies. So it's best to probably try and pick out a design that will have both of those pushed as high as possible, I would say. So for the very last thing, let's just compare two materials then with the exact same dimensions and everything. So let's compare 5 millimeter thick acrylic to 5 millimeter thick aluminum. That's really thick aluminum. This is probably not going to work very well. Aluminum that's that thick is pretty heavy, not very bendable, but let's see what it looks like when you turn it into a speaker. Oh, that's not actually as bad as I thought it was going to be. Well, I think it's not as bad as I thought it was going to be because the aluminum is free to bend. It's free edges with the corner stands. That's not terrible, actually. So here, again, let's move some of this stuff out of the way. So it doesn't really start bending until 145 hertz-ish. Let's see what's going on. Yeah, that's this. You know, so actually that's not horrible. I thought it was going to be a lot worse. But the coincidence frequency is really low. Yeah, you can see, here's the coincidence frequency. This is when the radiation starts beaming parallel to the edges and then starts to move inwards. So, not great. Let's, just as one final thing, let's compare that to like the worst possible thing in the world, which would be all clamped edges for this thick aluminum panel. Let's see what that looks like. I have a feeling this is going to not work very well. Generating new graphs as well. Oof, yeah, okay, this is what I thought was going to happen. So, we don't really have any bending motion on the panel until about 492 hertz. That's the first mode, that's this guy. And then you can see there's not really much radiation until 500 hertz here. And then even after that, we only really have radiation at these pretty sporadic little modes. And then the coincidence frequency happens right here, and then it starts to beam. That would be not a great sounding speaker, to be honest. Not good at all. Okay, so that was fun. Quick little exploration through some of these design parameters. You can go a lot deeper into all these things. Multiple exciters, different types of exciters, different materials, different shapes, different thicknesses, all sorts of different things. Lots and lots of different possibilities here. I'm not quite at the point where I'm ready to release this because I'm not sure exactly how I'm going to do it, but I'd love to get some feedback about what people think who are into making these speakers. I do make these speakers sometimes, but I am more in the role of serving as a consultant for companies that are making these speakers right now. So I'd just be interested to know what the community thinks of people who are into making these speakers. What would be useful for you? What changes I could make that would be useful? Or if you're interested in me simulating any specific design that you think of or adding anything to this, as long as it's not mathematically impossible for me to do, I'm happy to try and add things in here. So yeah, please let me know. And I'll post additional videos soon exploring some of these parameters in more detail. Thanks.